Gustave Eiffel University, so we don't move too far from the Paris location.
Okay, thank you, Mr. Chairman. So I will present some activities that we have on in the field of offshore geotechnics in the University of Gustave Eiffel, but I have to say that I have special glasses because I use my centrifuge modular glasses, so I will show only application in this field, which is the main activity that we have in offshore geotechnics as a whole in the university. So I will just say a few words about where I come from, and I will show some applications and then the conclusions. So we are here in Zurich, Paris is there, Nantes is on the west coast in the South Brittany. We can go by TGV very rapidly. And what I want to say also, it's not as history, of course, plenty of students. It has been a green capital, like the European green capital and European capital of innovation. Recently, we have nice landscapes, plenty of students, and we also have an exceptional concentration of physical modeling facilities. So, of course, the geotechnical centrifuge, I will come back later, but there is also in École Centrale de Nantes a towing tank and a wave tank for hydrodynamic applications. There is a wind tunnel in CSTB. So you can see a quarter of Paris, La Défense, on the picture with the cube, and a project of a high tower that has not been built finally. And we also have, for geophysical application, laser vibrometry bench, acoustic semi-anechoic chamber, also pavement fatigue carousel on the Uni Eiffel campus, and all the ones with the blue frame are part of a scientific group that we have created together with Ifremer and École Centrale de Nantes on marine renewable energy. So about the use of centrifuge modeling to offshore application. So we have plenty of examples. So I will choose only to present application on suction anchor, sliding foundations, piles, and I will speak about a recent and new project which is going on, the new tank project on mutualization of anchors. So our background in the field of offshore geotechnics has crossed a number of different companies on different offshore applications. So I cannot speak of everything because some are more or less secret, not published. And you can see that in the past we worked on oil and gas applications, and more recently we turned toward marine renewable energy applications. So about suction anchor, so I made some archaeological work and came back in 1994. So the first application that we performed in the centrifuge was to be compared with infield test performed close to Oslo in the Lysaker site. And those tests were performed by NGI and Exxon. And so they performed four tests with inclined and monotonic and cyclic loads. And in the centrifuge, so the model was this size, so at the scale 1/10, so 10 centimeters for each of those four caissons. And the tests performed were about on the site clay, the Lysaker clay, and on the space-wide kaolin clay, which is an industrial kaolin that we can find very easily. and which is used in most of the centrifuge modeling activities. So we had to simulate more, as much as possible, the conditions of the loading, so in-flight installation and loading, so without the centrifuge stop. So this is the drawing published by Morrison and al. in '94. And so there is an horizontal jack here that control with the pulley system the installation of the 4 caissons, and there is another jack for applying the load on the whole structures after the installation. And so there are also instrumentation, so you can see some cables and some sensors that are included here. So we have pore pressure sensors and displacement sensors and force sensor. So about the soil, so this afternoon we have seen some clay characteristics in offshore, and I have to say that in this site in Lysaker, the site profile show underrain cohesion up to 10 kPa only for 3 meters. And so we tried to reproduce to be in this site profile, but there have been one mistake. So it's a way of understanding of our mistakes. One profile with the reconstituted clay on Lysaker natural clay show a very higher underrain cohesion profile than expected. And when the pull-out tests have been performed, of course, the results were quite different. So with those results, we can see that first we have to take care about the reconstitution of the clay profile, and also that even if we use the natural clay from the site, which is quite complex to use because you have to collect it, to transport, to re-prepare, to dry it, to re-weight, and to compress. We can use industrial clay, which is delivered in powder and bags, like the kaolin clay, space white clay. So those tests were in the early 90s, so it's a long time ago. But it was really the first step in this field of offshore geotechnics. So we had the opportunity to test different suction caissons, so with different scale, with different slenderness, with application load here. In this case, they were applied at the top, but we can apply inclination. And more recently, and in this case, in a study for SBM Offshore, we apply inclined load, and the pile die where the chain is connected to the suction anchor is at 2/3 of the depth of the embedment of the caisson. So you can see that the mechanism is not so simple. There is both lateral displacement, inclination, and vertical displacement during the loading. So this is another view. And by the way, you can see on the left, there is a CPT which is waiting for performing a test, the small rod on the left there. Sorry? Thank you. And so we have another view of this test. Okay, so those pictures have been recorded at 60 G during the centrifuge test. So another example on which we worked with a special device, which is the 4-axis robot that we can use in the centrifuge up to 100 G, was the application of sliding foundations, for which we had the opportunity to use different tools with this robot in order to simulate this type of foundation I will detail, and also to have a T-bar test, and also laser scan for scanning the surface. So it was about pipeline and termination. So this PLET is a foundation. It's a system which is at the end of a pipeline and on which is connected other devices and possibly the riser that is connected to the boat, the FPSO that will collect the oil. And during the life of this deep water exploitation, the exploitation is stopped once a year, and so the pipeline, as it is full of hot oil, will when it will be stopped, the temperature will fall down, and so there is contraction up to few meters. So what happens on the foundation here? This foundation could be subjected to high loads, overturning moment, and tension load, and it was the idea developed by Subsea 7 here was to define this PLET as a sliding foundation. So it's like a small boat that can slide at the bottom of the sea during the exploitation of the oil in this zone. So this is the tool that we have developed. So it's a typical unique platform that we have at the top for a connection on the robot. And then we have here a lot of instrumentation. So we have a force sensor for vertical and lateral load. We have displacement sensors that are connected to the foundation. And we also have two pairs of laser sensor in order to measure the elevation of the soil in the front and on the back of the sliding foundation. So during one test, so the foundation is sliding slowly, and some soil is scraped from the surface to form a berm that will be more and more important after the different cycles. So we apply up to 20 cycles on this with this foundation, and so we measure the elevation of the berm cycle after cycle. And also there is some differences in between the heat up zone. So the first way we go on one direction, and the cool down where when we come back. So there are it's a non-symmetrical phenomenon due also to time of consolidations that we have to respect in between the movement. So I can go more quickly on about this experiment. So you can see that the berm is growing up during the life of this structure. Okay, so I move to monopiles, and for small-scale monopiles, we recently included instrumentation based on fiber optic. So it is based on the Bragg grating sensor. So the principle is that the fiber optic is graved at different places, and the light that comes from one side may be reflected or transmitted, and the analysis of the light allowed to identify the strain, local strain on each grating zone. So we worked on the case of monopile subjected to horizontal load. So with this instrumentation, we placed two fiber optic at the opposite on one diameter in order to be able to measure the strain in the direction of the horizontal loading. So the installation is quite easy. You have to place the fiber optic, and then so you can see the zone where one zone where the measurement is done, and we make a protection just to get the same diameter for the pile. So you can see here the model pile, and we apply here in this case. We study, in fact, the amendment of the monopile in this study, and we apply the load horizontally, so with different in different cases in the container. And so with this instrumentation, we can measure the sort of strain, local strain profile. And after calibration, we have the bending moment profile. And we also can see here that those profiles, well, there are different cases here, but those profiles are not exactly symmetrical. So there is a slight difference in between the zone compressed and the zone in extension. And this is due to the friction which is mobilized along the pile, which is different in each zone. And from those results, we can, by double derivation and double integration, obtain the displacement profile and the reaction profile, and then make some analysis on the PY curves. Another point that we developed is the in-flight installation for the monopile. So for that, we developed a new hammer, and the principle is that a mass is guided on a wave-shaped support, the green one here, and this mass at a certain moment will fall down, and so there is a shock, and we can apply the energy required. So we have some details here of the RAM and the support. And a small video here. So this is a 1G video, huh? So it's not, it's going very slowly, just to see the mechanism of this movement. And so we can calculate the cumulative energy. So we have quite good repeatability, and we can go up to 5D, so 25 centimeters in dense sand at 100 G in this case. And here I have a small video. It is a little bit accelerated by 60 times. So you can see here we are starting the centrifuge, increasing the G level. So you can see all the cables that move, that they are more and more heavy due to the centrifuge acceleration. And then the hammering starts. So we have a rapid displacement, and then slower and slower displacement due to the friction of the applied to the soil. And when the required depth has been reached, the hammer will be removed, and so without stopping centrifuge, of course. And then with another jack, so here an electric jack, we will apply lateral loading. So here you have a monotonic load, but you can apply, of course, cyclic load in this case. Okay. And some results about the installation effect. So we compared here the installation at 1G, so before starting the centrifuge, and installation at 100G by impact driving. So we have here the bending moment at the ground level and the rotation at the ground level. So you can see that the response are not very similar, especially at the start, where the stiffness is really different. So you can see the difference. So I have 1 minute, okay. So we have similar trends for horizontal load also, but also I wanted to say that for large displacement, the behavior is quite similar, because the soil has not been impacted so much by the installation if we mobilize the load far from the monopile. Okay, so we have difference also on the PY curves. I have an example also on helical piles. So helical piles are this type of pile, so with one helix in our case. So we install with a special device, hydraulic jack and electric motor that allow to screw the monopile, the helical pile, and we applied cyclic loads, and then after that monotonic post-loading, and so we can compare the initial monotonic load without cyclic load in black, and other cases. And so you can see that there is almost no differences. So the bearing capacity is maintained even after different sets of cyclic load. So I have to go very quickly. So we are starting a new project on mutualizing anchors. And the objective is to investigate the potential of shared anchoring to reduce the cost of energy from floating offshore. So it's a joint venture a group, if I can say. The budget is more than 1 million euros over 3 years, and it has been launched last year. So we spoke about floating wind turbines that can be connected all together. There is a project developed this year in Hywind-Tampen by Equinor in the North Sea, where you can see here the typical suction anchor that are where there are 3 chains linked for the shear anchoring in this case. So in this, well, it's a classical project with numerical application and physical modeling application. I would just say a word about physical modeling. So we will develop a new setup. So we received recently the jack, so it's not operational, but in a certain time, so we can apply loads at 120 degrees each one. And so the idea is to change the load path depending on the directions, and in order to identify the failure envelope under monotonic and also multidirectional loading, and to see the impact of cyclic loading. So to try to identify if there is stable, metastable, or unstable, and it's unstable zones in this case. So I skip to the conclusions. So we have since 1989 applications in the non-centrifuge. We are going from oil and gas to marine renewable energy. And so we have some new technological development, strong links with the industry. I have to acknowledge our partners and have some references of our works. And I want just to conclude on this information that we will host in Nantes the next ISFOG symposium, International Symposium on Frontiers in Offshore Geotechnics in 2025, June 2025. Thank you for your attention, and sorry for the delay.
Thank you. Thank you very much. Do we have a very quick comment